this is the answer you have. Why?
Carbocation.
That's good. Positive charge on carbon. Right? So you're going to go in depth. What is the difference between carbocation or carbocation or whatever you call radical and carboanion? So the carbon can have 3 different names. Okay? So let me focus on the carbon that has the charge over here, this carbon. And then for other CH3 groups, let me write R for easiness. Okay? So I'm going to draw the same species over here, like carbon, and then I'm going to have R, and then I'm going to have another R, and then I'm going to have the hydrogen. Alright? So let's say R1 and R2. So just to distinguish that, R or R prime, for example. So R prime going to be CH3, CH2 unit you have over here. Right? That's R prime, for example. And then CH3 you have on the other side. Let's say this is R. Right? So CH3 is R. Just for shortcut. Okay? So now, what's going to be the hybridization of that carbon? sp, sp2, sp3.
sp3.
sp3, right? So you have 1, 2 R's over there, and then 1 hydrogen. So you have 3 groups. So it's going to be sp3. Correct me if I'm wrong. sp2. All right. So this is going to be sp2. Okay. So sp2. So why sp2? So you're going to have few conditions to be out of sp3. So for sp3, just remember sp3 for the base. If you have carbon, and then you have all 4 covalent bond over there, this carbon is going to be always sp3. There is no exception on that. Right? So the reason is, you have the 4 valence electrons on carbon. If it makes 4 bonds, all going to be used, and then 4 other are going to be shared from the other atoms. Right? So all going to be the covalent bond, or you can call it the sigma bond for that. So if you have this condition in any hydrocarbon, that carbon is going to be sp3. Right? So you have the 3p orbital, 1s orbital, all mixed together to form 4 bonds. Right? So remember, you have the boxes like that. You have 2s, and then you have the 2p over there. So one box is gonna make 1 bond. You have 4 bonds over there in the carbon. So all 4 boxes should be involved in that. That's why it is sp3. That's the reason why. Okay? So now, if you see our charge or cation over here, so how many bonds you have? 3. You don't need 4 boxes for 3 bonds. 3 boxes is going to be enough for 3 bonds. Okay? So to make the bond, what you are doing over here is actually you are using this box and then 2 boxes of P. So all together 3 boxes, right? That's the one you're gonna make to form. You're gonna have to form the bond over here. So now 1 box is not used to make the bond, right? So what is that box? that box gonna be 2pg, right? So this is the box you have unused. P orbital oriented in the g direction. Okay, so remember you have the, in a Gen Chem you have like something like this one. If you have y, x, and then g axis, so x p orbital gonna be like that, and then y gonna be to the y axis like this, and then g gonna be to the g axis like that. You have three p orbital oriented along x, y, z, right? So one of these three, which is pg, is not used to make the bond. Okay? So that's where your charge is going to be there. So this is 2pg, which is not used. You have the plus charge over there, that means it doesn't have any electron there. Alright? So it is sp2. Okay? So this is how carbocation is going to be for every reaction. Whatever you see, if you see plus charge in the carbon, doesn't matter what the group you have, R prime, H, whatever you have. So the carbon is going to be always like this. You have the P2pg orbital empty without any electron in it. Alright, so that's the carbocation. So now, if I say a radical, for example, so let me give the same groups over there. So R prime, carbon, R, hydrogen. So now I have one electron there ready for. So then what's going to be the hybridization of carbon there? Exactly same thing like carbocation. The only difference is you're going to have the pure pg orbital like before. Now you have one electron in that. Okay, so before you didn't have any electron. Now you have one electron. That's why it is radical. Same hybridization, same orbital, same bonds, everything is same. Right? So now I'm going to call for that carbanion. Okay? So now I'm going to write another structure, the green label over here. So R prime, and then carbon, R, I have a hydrogen. So now I have the negative charge over there, say minus. Right? So you can have two electrons to make the bond. So these two electrons are going to be over here, minus charge. Okay? That means carbon has gained one electron from somewhere. If you have only one electron of the carbon, that is a radical, it doesn't have plus or minus there, because that electron was with carbon from the beginning. That's the valence electron. Okay? So now here, out of two electrons, one is the valence of carbon, the other electron came from somewhere. Okay? So it is negative. Right? So now what's going to be the hybridization? Same hybridization. Okay? So you're going to have the p orbital over here, like before. Now you have two electrons over there. So, to be sp2, you need to have charge on the carbon, either plus, either minus, or radical. If you have these conditions, the carbon is going to be sp2. Or you have the double bond. That's the obvious one, right? If you have the pi bond, you're going to have the sp2 hybridized carbon there. So that's the reason why C is answer. Right? You have the carbon, you have the pure p orbital on it. It is empty. So it is carbocation. Okay, so now if you have a question like which is radical, which is anion, now you can identify. Right? Good? All right. So, number 2, which of the following Hammond postulate is correct for endothermic reaction? So now don't only focus on the endothermic, say exothermic also. Right? So you're going to have 2 different types of reactions. When you have the heat absorbed by the reaction or heat produced by the reaction. So based on that, you're going to have exothermic reaction or endothermic reaction. Okay? So now, here, it is related to the Hammond postulate. Right? So let me draw the neutral one that we cannot answer. Right? Because can be either side. Okay? So I'm going to draw one profile like this. So I have the reactant over here, and then I have the transition state, and then I have the product over here. So I have the energy of reactant and product, same energy. Okay? So this is reactant, always on the left side, right? And then you're going to have the product over here. Okay? So now, if I ask same question, question number 2 for this reaction, it is very confusing. We cannot really answer unless some other guess is given, or factor is given, right? Because you have the same energy of the reactant and the product. You have the transition state exactly in between them. So we cannot say which is closer to the transition state. Right? So this is confusing. So simpler than that is either endothermic or exothermic. Okay? So now let me draw one diagram for the question. Okay? So now this is for the question. So you are endothermic reaction. So that means you have the reactant over here. So you're going to go all the way to the transition state, and then you're going to have the product over here. So product, right? So this is reactant. So this is endothermic reaction. Why endothermic reaction? You're going to have the energy of the product higher than that of reactant. Okay? So now you're going to see transitioning stage of the reaction, and then you're going to see which is closer to that. Or in other words, structure of which, either reactant or the product, closely resembles to the transition state. So whichever is closer to the transition state, that's the one going to have the closer structure, similar structure. Okay? So now you're going to compare the energy values. So the energy difference between the transition state and the product, you're going to take this value, and then you're going to compare that with that of reactant, that value over here. So obviously, the product is closer, right? So now you're going to answer the question. So you have options over there. Transition state will resemble the product, the reactant, both, none. So the product is close to transition state. So you're going to choose that. So A is going to be the answer for the question. Okay? Because it says the endothermic reaction. So now, I'm going to change this question a little bit. and then I'm gonna change that to exothermic reaction, right? So then which one you're gonna choose?
B.
So if you're gonna draw the structure for that, I'm gonna draw like this. I have the reactant over here. So it is exo. So that means the energy gonna release heat. So it's gonna have the lower energy than the reactant. Okay? Because it's gonna release heat. So now which is closer? Reactant closer or the product closer? Reactant, right? So if it is that, then the answer is gonna be that, B. Okay? So that's the Hammond postulate. So it's gonna compare the energies between the transition state and the reactant product. Okay? The same for the structure. So closer the energy you have, similar gonna be the structure of transition state and or reactant product. Okay? Good. So now, whatever form you're gonna have the question, you're gonna answer, right? So number 3. So you have the hypothetical reaction, A plus B, which are reactant, right? And then C, D, these are products. So for this reaction, it is given delta G, or the change in free energy, is greater than 0. That means positive. It is plus value you have, right? And then the reaction is favored to the left. It also say the equilibrium position gonna shift to the left. That means the reactant side, right? So if I draw this, actually what it is saying over here is a little bit to the right and then more to the left, right? So C plus D, something like that. So you're gonna have the more reactant there than the product, right? That's what it means. Okay. So now, what's gonna be the value of KEQ, equilibrium constant? So you can answer without the knowledge of delta G for this one, right? So if you say KEQ, that's gonna be product over reactant, right? That's the value. If you have coefficient, you're going to write the coefficient of the power of the concentration. So here it's not given, just write CD over AB, right? So now, what it is saying is that the reaction is going to go to the left. That means you're going to have more A and B. So, which is going to be greater? Denominator is going to be greater than the numerator. Because the question says it's going to go to the left. You're going to have more reactant there. Right? So now you can answer what's going to be the value of KEQ just on the basis of reaction goes to the left. So you're going to have the exact 1 value for KEQ, or you're going to have less than 1 or more than 1.
Less than 1.
Less than 1? Yeah, you're going to have more numerator, you're going to have less than 1, right? That's going to be the answer. Right? If it doesn't say either way, doesn't say whether you're going to go to the right or left, perfect equilibrium, and then you're going to have the delta G 0 at that condition, because we have the relation delta G equals minus RT ln KEQ. So obviously when you have the KEQ1, log of 1 going to be 0. So you're going to have delta Z 0 at that condition. Okay? So having KEQ 1 means delta Z going to be 0. Okay? So if you have the perfect equilibrium, doesn't go to the left, doesn't go to the right, you have the 50% product, 50% reactant, then that means you're going to have KEQ, the same value in numerator, same value in denominator, you're going to have 1. Okay? Delta Z going to be 0 there. So now, if I change the equation a little bit, and then I'm going to do this. So instead of that, I'm going to change that. It is less than 0, and then I'm going to say this to the right. At that condition, what is going to be the value of KEQ?
It's more than.
Obviously, more than 1, right? So if you have that, you're going to choose A. Right? So B is going to be the condition in which you have the equal product to the reactant. 50% exactly. So it is very hard to attain that, but if you have that condition, you're going to have KEQ exactly 1. Okay? So now you can answer KEQ and delta Z, right? Good. Ask me if you have any confusion. We have more time, I can explain even deeper. Good. All right. So now question number 4. So you have the free radical chlorination. So you have the chain reaction there, right? So halogenation of alkane. Remember, you have the initiation, propagation, termination steps, right? So it is which step you have? So you have the radical on the left side, you have the radical on the right side. So which is going to be that? Propagation, right? Propagation. So if you have the molecule on the left side, radical on the right side, going to be initiation. If you have the opposite to that, the radical on the left side, but the molecule on the right side is going to be termination, right? So you have the 3 steps there. So anyway, so you have that, but it is not asking which step of chain reaction it is. It is asking change in entropy. That's what it is asking. Okay? So delta yes. So you have the small circle there, that is the standard state. You have at 25 degrees Celsius, and the concentration is going to be 1 molar, and the pressure is going to be 1 atm. So these are the conditions for that. So it doesn't matter what condition you have. You can guess what is going to be the change in entropy. Okay? So, how are we going to guess it? You remember? That's going to be, so the number of product, so let me write product number, so get less confusion, so otherwise. So this is going to be number of products. You're going to say sum of that if you have more than 1. So take sum of all the product you have, sum, right? Minus number of reactant. So we're going to do that, right? If you have the more product molecule, delta S is going to be positive. If you have more reactant, delta S is going to be negative. If you have the equal reactant, equal product, it's going to be 0. Right? That's what it means. Right? So now you're going to count it. So how many? You have 1, 2. So you have 2 in the product. And then in the reaction you have 1, 2, so you're going to have 2 there, so 0. Right? So you don't have any change in entropy. You have the same number on the right side, same number on the left side. Right? So remember, you're going to do right minus left, product minus reactant. So that's how we're going to do it. So this is going to be this one, right? You have the 0. So that means, that means in terms of entropy, it doesn't say anything about the reaction. You're going to see the other factors for that. Enthalpy, free energy, entropy. Remember, you have the 3-factor correlation equation, so you're going to see the other factor. Okay? But actually, you have this in the next question over here.
Professor?
Yep.
I have a question about that one. So if, for instance, in the reactant side it said 2Cl, would we still count that as 2, or would it be still be 2?
If you have 2Cl, you're going to count this too. So you mean like that?
Yes.
Or you mean like that?
The first one.
So these are different on that. Okay?
No.
So for the second one, you're going to count 1. This one, you're going to count 2. Just like that.
Okay.
Size doesn't matter, number matters. So now, number 5. So actually it is tied to the first question. Wait a minute. So which of the following correctly expresses the just free energy change and then enthalpy and entropy? So this is noted by letter S, enthalpy going to be letter H, and then this going to be letter G, right? It says the change. So change means you're going to have the delta, right? So that's the change you have. Okay. So now, what's going to be the equation? So delta H minus T, that is temperature, times delta S. Okay, so that's the one you're going to choose. Okay, so the just energy is the difference of enthalpy change minus the entropy change. So the difference, so you're going to have the minus. So now number 6. So you're going to have the bond broken or formed in any reaction. So how are you going to classify based on the strength of bond making or breaking? Okay. So for example, let me write the hypothetical. A plus B, let's say A2, B2, 2AB, like that. Right? So hypothetical. Right? So general, I mean. So you're going to have the A and A, that is A2, you're going to break that bond to make the product. And then you're going to have B and B, you're going to break that too. And then you're going to make the bond between A and B. Right? So for this reaction, you have 2 types of bonds. So one is going to be the breaking. So you're going to break that, you're going to break that. And the other going to be, you're going to form that bond, right? Right, so you're going to have this scenario in every reaction. Right, so one thing that you're going to remember always, does not matter what type of reaction you have. Always, the very common thing is, whenever you form the bond, energy is released. Always. So it's gonna give the energy out from the reaction. Always, whenever you have the bond formation. Okay? So how much energy? That's the question. Some gonna release very small amount of energy, some gonna release large amount of energy. Right? That depends on the strength of bond. If you make the stronger bond, more energy gonna be released. Or more heat gonna be released, you can say that way. Right? So heat is form of energy. So stronger the bond formed, more energy gonna be released. Okay, but always energy gonna be released when you make the bond. Right? So this is one factor. Other, when you break the bond, then the system gonna absorb energy. You need to supply energy. Either you're gonna hit it, or you're gonna use a catalyst, or another form of whatever assistance you're gonna supply there to break the bond. Right? So energy gonna be absorbed. So energy is absorbed by the reaction or system, whatever you want to call it. So if you recall, there are two systems surrounding, right, at the boundary. So you can say system as a common, but this is reaction. Okay. So now the question is, in the reaction, if you have both happening at the same time, now you have the competition. Okay, so if you have only one happening, if the bond is forming, then obviously it's going to release the energy. If bond is only breaking, of course it's going to absorb the energy, right? But if you have both in the reaction, so now you have the competition. So the question is, which bond is stronger? The bond between the reactants that you're going to break it is stronger, or the bond is formed to give the product is stronger? That's the question, right? So whichever is stronger, they're gonna control overall process. So now it says here, clue, the stronger bond are broken. So that's the clue the question gives, right? So that means you have to break the stronger bond. The reaction is going to absorb more energy than the weaker bond is formed. Releases less energy. So what's going to be the overall difference? The system going to absorb energy, right? So system going to absorb 2 joules, for example, to break the bond. So you're going to have 2 joules over here. And then it's going to give only 1 joule when it forms the bond. So what is the overall? 2 minus 1, 1. 1 is more absorbed. Right? So now which type of reaction? Is it endothermic or the exothermic reaction? Endo, it absorbs the energy, right? So you're going to choose endothermic reaction for that. Okay? So now, I'm going to change a little bit. So to make it a little bit tricky, okay? So I'm going to say, so different color, okay? So focus on the green color over here. I'm going to say weaker over here. And then I'm going to say the stronger over here. Now what's going to be the answer? Just by changing these 2 words over there.
Exo.
Exo, right? So we have that. That's going to be exothermic. Because the overall energy is going to be released out from the reaction, which is exothermic reaction. Right? All good? Okay. So now we're going to go to next. So this is about kinetics. So we have the reaction given. So this is reaction. You have alcohol, alkyl halide. You have, so you have the product CO, so carbonyl compound, ketone, right? And then SBr, you have the byproduct. So this is the reaction given. Okay. So now, experimentally, when you do this experiment, what you find is that you're gonna change the concentration of reactant, and you're gonna see the effect in the speed of reaction, rate of reaction. Okay. So now, what's gonna be the rate of reaction? So let me write the rate. Rate of reaction is gonna be equal to rate constant you have, that's the constant value for a particular reaction you have, and then you're going to write the reactant, right? So you're going to have CH3, 3CBr, this is one reactant you have, and then you're going to have another reactant, CH3, CH2, OH. Okay, so we're going to write all reactant. Doesn't mean that the reaction can depend on all. Sometimes may not. Sometimes it can. Okay. So now one factor is missing over here. What's going to be the power of the reactant concentration over here? So let me write N1 and N2. Okay, to make this easier. So far we have not read the question. So this is going to be the standard rate of equation, right? So now let's see the clue given in the question. Okay, so what it says? It says one finds that if the concentration of this alkyl halide is tripled, if we make the 3 times more concentration, right? So what's going to be the effect on the rate of the reaction? So it says it also triples, right? So that means now if you do K, you're going to do 3 times the concentration. We're going to do 3 times over here. So 3 times the concentration of that, 3 CBr. So now I'm going to have this 3 with the power over here. Remember, 3 is part of the concentration. So you're going to have the power N1 also for 3. Right? And then you're going to have the same concentration. Oh yes, N2. Right? So now you're going to take these 3 out. Right? So you're going to have the 3 to the power N1 when you take out, right? So if you have N1 equals 1, then 3 power 1 is going to be 3, okay? So N1 is going to be 1, right? Or 3, 1, okay? So then what is going to be the order of the reaction with respect to this molecule?
First one.
No, just with respect to the first molecule. We are not taking overall. Okay? So for the alkyl halide, 1 lead. So you have N1 value 1, right? That is the first order with respect to alkyl halide. And then, now let's see the second one. So we have the second clue. If the concentration of alcohol is doubled, the rate of reaction is unchanged. Right? So that means, now, if I do 2 times CH3, CH2, OH. So remember, you have the whole power N2, right? So now 2 to the power N2. So doesn't change means this has to be 1, not to be changed. In which condition you're going to have 2 to the power n2 going to be 1? When n2 is 0. So you're going to have 2 to the power 0 going to be 1. So n2 is 0. So this is based on the clue given there. So now you're going to say that the rate of the reaction is first order with respect to alkyl halide, the first reactant. The reaction is 0 order with respect to the second reactant, which is alcohol. Now what is the overall? So you're going to say 1 plus 0, that is 1. So overall rate of reaction is going to be 1. So that's how you're going to answer, right? So now let's see what is asking. Which of the following correctly describes the kinetics of this reaction? So remember, we have up to this point, without just reading the option over there, what are the things we know? The reaction is first order with respect to the first reactant. It is 0 order with respect to the second reactant. And then it is first order overall with respect to all the reactants you have. So you have the 3 things known from there, right? So now let's see the options, what you have there. So the reaction is third order. So you don't have third order. So this is not the option there. And the reaction is first order. Yes, it is first order. But with respect to which? The first reactant, not the second reactant, right? So this is not. You have 0 order with respect to that, not first order, right? And then the reaction is second order overall. No, 1 plus 0 going to be 1. That's the first order. So this is not the option you have. And then you have the reaction is first order overall. Yes. You have the 1 plus 0 is 1. So overall it is first order reaction, right? Because it is independent on the concentration of the second reactant. So why it happens? You can have the second reactant as a solvent. So you have a lot of, like 99% you have second reactant, and then you're going to have very few first reactant. So the concentration of the second remains virtually unchanged. So it doesn't depend on that. Okay? So you're going to have this answer. Good? Yep.
So I understand how we get the overall reaction and finding the order, but can you quickly re-explain how we got the reaction orders for the two separate ones?
All right. So let me. Do you want me write with respect to this one or the general? A, B, C, something like that.
Just
Okay, so let me say in general, okay? For all reactions. So suppose you're gonna have, let me write in the red color. Yeah. So A plus B gives product P, for example. General, can be any reaction you have. Okay? So I'm gonna take the same condition given in the question over here, right? So for A, if you triple the concentration, the rate gonna triples. So if A gonna be changed to 3 times A, right? So you're gonna have the 3 times the concentration of A. So what you're going to write is, for the rate of the reaction, you're going to write A, so you're going to have K over there, A to the power N, and then B to the power N1, N2, let's write the same as before, N2. That's the rate equation, right? So what I'm going to do is, now I'm going to write 3A to the power N1, and B is not changed, that's N2. So you have K over there, right? That's the rate equation. So the equation says you triple the concentration, that's why I write 3A over here. If you say double, I can write 2A. If you say 4 times, I can write 4A there. Okay? So you say 3 times of A in the second trial, so I'm going to write 3A there, right? So now, after changing this, if you compare a rate, let me say R1 over here, so R1 value and R value, so R is before changing to 3A. R1 is after changing to 3A. If you compare these two, what do you have? You have 3 times. Okay? So R1 is 3 times more than R you have. Okay? So now the question is, to be 3 times, what going to be the value of N1 you have? So for the second, you can disregard that because you have the same as before. It doesn't contribute anything. You have the same values, right? So now the question is, what is going to be the value of N1, which is the power, so that your R1 going to be 3 times 2R. Okay, so you're going to choose N1, let's say 0, let's say 1, let's say 2, 3, 4. Just plug the value and then see what's going to be the result. Okay, if you put 0 for N1, what's going to be the value of R1 there? So power 0 is 1, so you're going to have just K. You don't have any concentration there. It is independent of the concentration. Doesn't say that, right? What if you have 1 there? So you're going to put power 1 over here. So you have the same A power 1 as before. And then you have the 3 power 1 is 3. So you're going to have the 3 times K times A. Now you have 3 times the rate as before. That's why it is 1 order. If you have 2, what are you going to have? 3 power 2 is going to be 9. So you're going to have the 9 times the rate compared to the first one. Okay? So that's why it is first order. That's the reason we're going to ask. Right? All right, done? Let's answer one question and then we're going to be done. Okay? So otherwise, we cannot finish all on Friday. So question number 8. So you have the profile given over here. So you have the X2G overall. So you have the intermediate Y. Okay? So which step has the lower energy of activation? So remember, in the one step reaction, you're going to have only one energy of activation. Okay? So the more intermediate steps you have in the reaction, that many number of EA you're going to have. Okay? So you can split that in 2 halves. Okay? So for the first one, first barrier, you're going to take the height of that, EA. So this is EA1, for example. I'm going to call 1 for that. And then for the second one, remember, it is based on the reactant. Okay? So be careful with the starting energy. So EA2 gonna be that. So for the second step, your reactant is Y. For the first step, your reactant is X. So for the first EA, you're going to take the difference of energy of X to the transition state. That's the EA1. And then for the second step, you're going to take the energy of Y, which is reactant for that, and then you're going to take up to the transition state, right? So now you're going to compare these two, EA1 and EA2. Of course, EA2 is higher, right? So that going to have the higher energy of activation, but it is saying lower, right? So lower going to be the first one. Okay, so X to Y going to be the lower, right? Okay. Good. All right.